I'm delighted to introduce Tim Ruchti. I've known Tim for many years now. He is Director of Algorithms at Nihon Kohden Digital Health Solutions. We began our time together when he contributed enormously to AI education and biomedical engineering at Johns Hopkins. And we've continued our relationship and work at the Ru Institute in Portland. Tim is a world leader in machine learning applications in healthcare. He brings to this a remarkably broad perspective gained in working with many, many different collaborators as a part of Nihon Kohden. So delighted you're here today, Tim.
Well, thank you, Ray. I appreciate the invitation to speak. I appreciate all of you sticking around to listen, and really want to say it's a privilege to be able to contribute to the discussion on AI in precision care medicine. My talk is going to be a little bit different than the last one, which was exceptional and thought-provoking. I just got to figure out how to... Here we go. I'll be talking about a specific area of application of artificial intelligence in primarily the clinical setting, and that is the prediction of adverse clinical events using continuous data. I firmly believe that this is going to be standard of practice in the future. And the reason for that is there is benefits to the clinician, there's significant benefit to the patient. There is data that has not been tapped for its full potential, and that is continuous data from cardiorespiratory monitors. Not to diminish other data sources, but I think there are key advantages to this data source that I'll talk about in a few minutes that lend itself to continuous prediction of adverse events. And then finally, there are solutions, solution platforms for deploying these types of models. What I would add is that it's important during model development that model development begin and end in the clinic. That is, pick a solution that is worth solving for a clinician. And then secondly, during the development process, consider how that solution is going to be integrated into the clinical setting. And that's exactly what the leading edge research at Ru Institute under Ray Winslow has done. They're conducting research in collaboration with Maine Health and Nihon Kohden that began with discussions with clinicians to identify important problems that were worth solving, problems that would impact patient care. And in addition to all of the innovative technical work that's being done, the team is also innovating in the area of clinical integration and user interface development. So the problem we're solving is the data overload problem. And our methodology in this particular case is prediction. Now, what do I mean by prediction of events? We want to be able to tell clinicians something that they don't already know. If a clinician has already recognized, based upon vital signs that are way out of range, oh, my patient's deteriorating, it's not going to be helpful to say, I've got a prediction, it's very likely that your patient is deteriorating and an event is going to happen. But rather, we want to detect the very subtle signs of deterioration that occur across vital signs through shape and morphology changes in waveforms that are consistent with a future clinical event, and thereby be able to inform clinicians something that they don't already know. Now, there are clinicians that are very adept at identifying deteriorating patients, but unfortunately, they're not able to monitor all patients through all time. Well, AI and machine learning can. And in fact, AI and machine learning has access to variables and metrics that clinicians don't have, and can bring the same standard of care, that is the same predictive performance, across all hospitals. And there's also significant benefit to patients. And the reason for that is adverse clinical events are associated with worse outcomes. In this bar chart, you see that patients in red who experienced an adverse clinical event had a much higher mortality rate than the patients represented by the black bars, who did not. And so our value proposition is, let's inform clinicians early so that they can make decisions about proactive treatment and thereby reduce the number of clinical events or adverse clinical events and improve outcomes. So that's the value proposition. I've mentioned a couple times data from continuous bedside monitors. I think most of you have seen something like this. Each rectangle is a patient. The scrolling data, our waveforms, the vital signs are on the left side. Here are some of the advantages to using this form of data in predictive models. One is data collection's automatic. No additional tests have to be performed. Measurements are continuous, so a model can be updated through time. And then data are an objective indication of patient physiology. And by this I mean a clinician did not have to order an additional test. This is data that does not represent clinical recognition or clinical suspicion, but rather is data that is collected directly from the patient. And as a result, models built on continuous cardiorespiratory monitoring data alone tend to generalize much better than other models. And the speaker right before me pointed this out, a model that was developed on EMR-based data. When practices changed, there was significant bias in that data. Well, unless patient physiology changes or we go from one patient population to another, the bias in a model developed on this type of data tends to be relatively low. And this data is also information rich. And for those who are not familiar with continuous data, here's a couple examples. Here we have 5 days worth of continuous heart rate data that's collected. The red dots represent the data that was collected by nurses and put into the EMR. So in that rectangle area, there's about 13,000 continuous points from heart rate. EMR only had 4. So the time series and the patterns in it are information rich and are ideal for the type of technologies we've now developed. We can go a little deeper though and look at the waveforms, because the heart rate is a feature derived from a waveform data. The RR interval of that waveform, the series of RR intervals, are highly correlated to patient state and patient deterioration. The morphology and metrics derived from this waveform are also highly useful. So how do we make predictions in real time? This is it's a very high level diagram, but yellow represents the current time. So at the current point in time, a window of data from the past is provided to a prediction model, and it might be 30 seconds, it might be 30 minutes, it might be the entire patient encounter data set. It's provided to a prediction model that creates a risk score, and of course what we want to see is that risk score increase through time prior to the event so that a clinician can both see an increase and a magnitude that my patient's at higher risk for this particular event. So I've got a couple different examples I want to show you, and they span a wide range of types of machine learning models. The first is a prediction of emergent intubation, and it's based on feature engineering and classical machine learning. And I chose this because this model has been deployed as part of an application, and it's an application called Comet that is part of Nihon Kohden's risk prediction system. The emergent intubation model is actually the y-axis on this interface. Now, what the Comet-like icons show is how the risk, the patient's risk profile has changed over the last 3 hours. So for example, the patient in bed 86 has experienced a significant increase of future emergent intubation over the last 3 hours. The second example is sort of bleeding edge research, and this is the prediction of cardiac arrest based upon a PPG foundation model. So in regard to the first example, I'm showing you one way that features can be engineered from ECG waveforms. The RR intervals of the ECG waveforms, that time series of information are highly correlated to the state of the patient, and that's illustrated by the plots on the right, which are the time series of RR intervals versus time. Now, the patient on the top experienced AFib. The middle patient is normal, and the patient below that has normal sinus rhythm for the most part, but has heart failure. So you can see in the patient on the bottom, their variability, that is their heart rate variability, is substantially lower than the other two cases. So the model that predicts respiratory failure uses heart rate variability and heart rate dynamics in addition to statistical time series features derived from vital signs. The model itself was developed long ago. I mean, this model was developed in 2016 using nonlinear logistic regression, but it was more recently tested on a cohort of 8,000 patients from UCSF. So you can see this is a substantially different cohort, substantially different time frame, and substantially different geographic location. The area under the receiver operator curves were equivalent in the 8,000 patient cohort. And what I'm showing you on the left is the plot of the risk score, the average risk score versus the time to the event. So the event for all patients who experienced emergent intubation, that event is lined up on the right side. The average risk score increases systematically on average prior to the event and provides at least 10 hours prior warning on average for the emergent intubation event. So the second example, this is provided by Saurabh Katari, who we collaborate with. He's part of Emory University. He's developed a PPG foundation model that has been fine-tuned to many different tasks, including in-hospital cardiac arrest. So this is what the model looks like. A PPG waveform is fed into a foundation model. That foundation model was developed independently on about 6 million hours of PPG waveform data. After the development of that model, a smaller data set was used to train the bidirectional LSTM, the recurrent deep neural network, to predict the risk of cardiac arrest. And I should note that the concept here is let's use the same architecture, the same technologies to develop foundation models that understand physiology, the same way that ChatGPT understands language. Here are recent results. These are results from a holdout set, so it's a relatively small data set from the same cohort as the training set. But what you'll see is the plot of the AUC versus the time prior to the event increases systematically up until the cardiac arrest event on the far right. And in fact, 9 hours prior to the event, one of the two models that's shown here, the one in red, has an AUC of about 0.8. Now what's also interesting about this plot is that the bigger model, that is the one in red, has 1 billion parameters, performs substantially better than the smaller model with 345 million parameters. And this is something that we've seen throughout the literature, the NLP literature, and it also seems to be consistent here, where the more data in the bigger model produces better results. So we understand we can predict these events, and there is a physiological basis why events can be predicted. The question is, when we make predictions and we clinically integrate them, can we improve outcomes? There isn't a lot of research that makes a compelling case on this. I'm going to show you one paper that looked at the product you see here, which is called COMET. It's a retrospective study that was conducted on continuous or contiguous encounters in the surgical ICU at University of Virginia Medical Center. So it's a before and after study of about 4,200 patients looking at 3 different outcomes: septic shock, this is mislabeled as sepsis, intubation, and hemorrhage. COMET was shown in the surgical ICU, was not shown in the medical ICU. So the medical ICU was used as a control. What you see is that in every case, the outcome improved, although the only statistically significant improvement was septic shock. But that was a reduction of 50%. So a fairly promising improvement in outcomes as a result of a predictive model and a methodology to clinically integrate it. And that brings me to the last part of my talk. In the area of predictive modeling, we do see a lot of research and a lot of papers, but adoption is lagging. Even though I'm very optimistic that in the future, predictive modeling will be integrated into monitors and into workflows to better inform clinicians, yet today, despite a mountain of literature, very few applications have actually been clinically integrated. And one of the reasons for this is that we lack platforms that enable both clinical integration and clinical deployment of models. And in fact, this was the number one problem I noticed when I first started working for Nihon Kohden, is we wanted to work in the AI space, and I asked, well, where will we get data? And then I asked, okay, once we build a model, how are we going to deploy it? And what we don't want to do is build a brand new software stack every time a new model is created in a brand new application. Instead, we want to use reusable platform. That reusable platform is depicted here. This is also what we're using with Ruchti Institute and Maine Health. The far left represents the hospital network. The data from that network is sent in an unnormalized way into the digital health platform. Digital health platform does two things primarily. One is it normalizes the data and stores it in a patient-centric manner to support researchers. Secondly, it has a stream processing engine that provides a live data stream of normalized patient-centric data to applications. So for example, I could deploy a clinical algorithm, and this is represented by the far right rectangle. I can deploy any Python-based model by simply changing a configuration file and subscribing to a particular data feed. So very easy to deploy models. Once a model is deployed, the results from that model feed right back into the digital health platform and then are distributed throughout the ecosystem. So if a researcher wants to deploy a model and display it in the central nursing station represented in the bottom, they can. Well, that brings me to my conclusions. I do believe that there is a great future in predictive modeling in the hospital, and it's because clinicians will benefit and patients will benefit. Thank you.